Okay, Assalamualaikum. So today we are going to learn chapter 3, which is new chapter gas absorption. Okay, so before we proceed, let's see the course learning outcome for this chapter. First, you are able to describe gas-liquid equilibrium for ideal solutions according to Roth's law. Differentiate packed and plate tower. So we have two towers here, packed and plate. And then explain in the packed tower the use of the packing materials and flow arrangements in packed tower. And then calculate the packed tower diameter, height of an absorption towers. Okay, these two calculation for the height is for the packed tower only. So for the remaining plate tower, so we are going to make a calculation for the material balance and calculate the number of theoretical stage in multi-stage counter current operations of a plate absorption tower by a graphical method. And then lastly, the demonstrations of effective teamwork and communication skills. So the requirement for this chapter is so you are able to differentiate between two tower. Here we have pack and plate tower. So for pack, we are going to calculate the height, and for the plate, we are going to calculate the number of stages. So this is the demonstrations of the tower, gas absorption tower in the plant. Even though it look like the same as the distillation column, but the operation is different. So the topic for this chapter will cover on the definitions, applications, and notation that is used in the gas absorption process. And then the gas liquid equilibrium for ideal solutions according to Roth's law. So we will see since now we will involve of two different phases of the gas and liquid. And then we will see the equipment and descriptions for the gas absorption column. And then we go for the packed tower to describe the packed tower and their flow arrangements. And then we will see several packing material that is used in the packed tower. So we will explain on their descriptions of the packing tower with their flow arrangements. And then we need to calculate the pressure drop and flooding impact tower determinations of tower diameter. So from here we can calculate the diameter of the tower and also the height of the tower. And height. Okay, so for the plate tower, so you are able to explain the plate tower, and then we calculate the stages here, stages of the plate tower. Okay, before we go further for their calculation, so we need to understand about the gas absorption process. So gas absorption process is a mass transfer operation in which one or more species a solute is removed from gaseous steam by dissolutions in liquids. So that means here we have our solute. So we use solute as our A. It must be in a mixture state B. So both of them here is a gaseous mixture. So comparing to the our distillation, it only involves of two components. So here we have another component, our C, which is our solvent. So dissolvent is in the form of liquid, whereas our A and B is in the form of gases. So this is one of the difference between the distillations and gas absorption. So the insoluble component present in the gas which is not absorbed is called the carrier gas, which is your C. So your C doesn't involve in um, the um, doesn't soluble in your gaseous mixture. So it just act as the carrier gas. That means the purpose of the C is to separate your A and B. So we're going to separate A and B. So we will obtain our A. We are interested in our A. Okay, so the transfer. So since we are going to separate A and B, so that means there will be a transfer of the component A from a mixture of AB. So how it happens is the transfer is based on the differential solubilities of solute in the liquid solvents. That means your A is soluble in C. So but your B is not soluble in C. That's how the separation can occur. So at the end, your carrier, okay, so at the end of your C will be with your A. So examples here is the removal of H2S, which is your solid, usually your A, from a natural gas, which is your carrier, gas B, mixtures of AB, using suitable solvents such as aqueous solutions of an alkanol amine, which is your solvent C. An intimate contact between the gas and the liquid is achieved in a suitable equipment or device like back column, tray-column, and spray tower. So the reverse of the absorption process is called as desorption or sweeping. So as the conclusions, in the absorption process, there will be a mixture of gas A and B, and also another component of C, which is your solvent, and your A and B is in gases, your C is in a liquid. So the separation can occur because of the preferential solubilities of solids A in the liquid solvent C. So other applications of the gas absorptions is many. So we'll see. Among the applications for the environmental, including of the removal and recovery of ammonia in fertilizer manufacturing. So since ammonia gases is usually produced from the gas processing plant, so usually we collect the gases to be used in the fertilizer manufacturing. And then we also want to control the emissions of CO2 from the combustion sources. Also the other gases from the rendering plants and the removal of the acidic gas CO2 from air. So the important terms that you need to determine is there are four things here. We had our feed as absorbents, which exists as a mixture gases, where they need to be extracted from the feed. Our solvent, which is absorbent, is the liquid, which is the P is convex, or you call it as C, your C. So the extract is the solvent, rich product. That means here we have our air air. For the raffinate is the residual gas mixture, the solute has been removed. So there will be remaining of air at the raffinates, but most of them have been. Okay, the widely use of solvent. There are lots of solvent available in the industry, including of the water, hydrocarbon oil, or aqueous solutions of acids and bases. Okay, that's all.